Friday, everyone. So today we get to talk about sleep, which I guess is kind of an unfortunate topic because you have to sit here and not sleep during it, but hopefully we'll keep it fairly interesting. I find this a very, it's cool to think about as a topic. We have a lot of sort of gaps in our knowledge. There's a lot that we don't quite understand about how things work. So we're going to end up presenting a lot of different possible theories, and we're going to be left at the end with, we're not quite sure which theory is best, but at least we have some basis of what might be going on. So you'll start seeing that trend as we start moving through this section. But we're including sleep in this chapter on consciousness because we think of sleep as an altered state of consciousness. So when we're awake, we are aware and able to interact with our environment. When we're asleep, we are unconscious. We are not interacting with our environment, at least not very much. And so the process of sleep regulation is actually a very complicated one. So we're going to pick a very simplified version for this class. I've done entire lectures that spanned a week and a bit on just regulating sleep, specifically on circadian rhythms and the genes involved. So to condense it down to like 2 slides is quite the challenge. So we're going to focus in on the fact that sleep is regulated by our suprachiasmatic nucleus, or SCN, and that's that tiny little red spot right next to our hypothalamus. So that's our control center that signals to our pineal gland that it needs to release melatonin. So our pineal gland is something we had talked about previously because one of our early sort of theorists had thought that that's how our sort of separate mind process connected to our physical body. But in fact, our pineal gland is involved in releasing melatonin that helps regulate our biological clock. So if we think about this biological clock as sort of a daily cycle that we go through, it involves sort of being asleep and then being awake, but it also involves other factors. And so we can call this our circadian rhythm. So circadian just meaning daily, and then the rhythms meaning that it's cyclical. So in this diagram here, we actually see 2 separate days. So we go from noon to midnight and back again, sort of twice. They haven't done a fantastic job with accurate labels on this, but that's fine. So we can see here that we're awake for part of the day, we're asleep for part of the day. And as we cycle through that, we see changes in body temperature. So when we're awake, our temperature gets a little bit higher, excuse me, and then when we're asleep, our temperature gets lower. This is a good time to note the axis because that's showing us that we're moving sort of plus or minus 0.4 degrees Celsius. So that's not a massive swing. So a good idea to keep in mind that it's just a little bit of a shift. So not as dramatic as it's set up to look like. We also have sort of differing levels of melatonin in our bodies. So we have sort of increased levels of melatonin just before we fall asleep, and then they start decreasing right before we wake up. So that's that release from our pineal gland. And the way that this is set up is that we have sensory receptors, not quite our eyes, but something that reacts to light similar to the ways that our eyes do. And that lets our brain know, and specifically our suprachiasmatic nucleus, know that that is the start of our day. So those light cues are part of what sets up this cycle. So when we have exposure, especially to blue frequencies of light, that tends to trigger that sort of awake feeling. So if you've ever seen those SAD lamps for seasonal affective disorder, they help by sort of resetting that biological clock, getting you bright light that helps start this process again. And so every morning when we wake up with the sun, it's resetting and setting off all of this biological cycling. The interesting part is that our natural biological clock is pretty close to 24 hours, but not exact. We run a little bit long, and so if we were left to our own devices with no light, then we would shift a little bit and sort of unsynchronize with the sun, but every time we are exposed to light in the mornings, we get to reset, and it kind of fixes it. So it's like evolution got us as close as it could to our natural day cycle, but it's a little bit off. And there are a bunch of really neat mutations that can affect individuals' biological clocks, They can make them run longer or shorter, and they can be sort of more or less sensitive to light, which is very, very cool. All right, so if we're going to be talking about stages of sleep, we should probably remember how we actually access and measure those different stages of sleep. So most of the measurement's going to be done through electroencephalogram or EEG. So we've seen these before. This is a nice close-up image of an EEG cap. So little electrodes that'll connect to the surface of the skull. And what they do is they'll usually put some kind of gel so you get good contact with the skin. And the intent is to measure electrical activity on the surface of the brain. We also see in this image something right next to the eye there. And that isn't necessarily part of that EEG cap. That might be an electrooculograph. And if we look at the roots of these, so it starts with electro, ends in graph. Okay, so we're still measuring electrical signals. It's printing stuff out in a format that we can read. The oculo part tells us it's looking at our eyes. So that's measuring the muscles around our eyes to see when our eyes are moving and how intense those signals are. We can also have electromyographs, myo for muscle, and they just measure muscle activity throughout our body. So all very, very good things to keep track of when we're trying to study sleep if we want to know what our brain is doing and what parts of our body are active and moving as time goes on. So we're going to be talking about each of 5 different stages of sleep. And so to reorient ourselves with these electroencephalograph printouts, these EEG waves at the bottom here, we have along the bottom axis is going to be time. So that's just a blanket measure of time. They've given us how long 1 second is. It doesn't really matter too much for us. Our vertical axis, our y-axis, is our amplitude. So that's the energy in the wave. So if you think back to our talk of sort of time and amplitude for looking at sound waves, same basic concept because we're looking at cyclical outputs here as well. And so when we're looking at these, what we're going to care about is what is the amplitude or how much energy is contained within the waves that we're looking at, and how spread out are they? Do we have sort of a really long wavelength or a really short one? If they're really short, we might say that it's high frequency, so we get lots and lots of waves in a short period of time. Or low frequency if they're spread out, because you get very few waves in a period of time. So that's how we're going to read these. And then we're going to go through each of our different stages and talk about what those waves look like, which particular traits let us know what stage we're in. And so we're going to present these as sort of a hard line between these different stages, but in reality it's a little bit more blurry as we transition from one to the next. But we'd say that we're in that next stage whenever we've hit sort of those milestones that are typical of that stage. And I'll point those out as we go. So at the top here we have our awake/alert EEG. So that's just beta waves. So we see lots of fairly close together low amplitude waves. And then as we start to relax, as we get drowsier, we transition over to alpha waves. So a little bit higher amplitude, a little bit lower frequency. They start to spread out a little bit, but nothing too interesting quite yet. So when we get into our stage 1, the first of our sleep stages, this is when we're just starting to fall asleep. So it's our transition into light sleep. And so those alpha and beta waves that we had in our wakefulness switch over into theta waves. And so you can see highlighted over there, we have some reasonably high amplitude and very low frequency waves that are labeled. So that low frequency, that longer wavelength, tells us that we're having fewer peaks of energy. So less firing. So those theta waves are what tell us that we've started into stage 1. And during this stage, this is when you might have a hypnic or myoclonic jerk. So that's that sort of jump feeling that you have when you start falling asleep and then your body sort of jerks you awake. Maybe you sort of thought you were falling off of something. That could be some hypnagogic imagery as you're just falling asleep. The idea is that your body is probably trying to make sure that you're not actually dying. So it sort of misread some of the signals, and your slowing heart rate was interpreted as dangerous, so it's just checking. but I'm not sure that's a 100% known. When we move on from our stage 1 into stage 2, we only spend a couple of minutes in stage 1. If you're really, really tired, you can drop through it in as little as a minute. If you're sort of having trouble falling asleep, it can take longer. But then we're going to drop into a deeper sleep. And so this is sort of the 10 to 25 minutes after you've started sleeping. So this is when we start seeing much more deceleration in those brain waves. So we can see stage 1 on the top, where we started seeing a couple of theta waves. Stage 2 is mostly theta waves. So we have lots of spread out, sort of lower frequency waves there. Our heart rate starts slowing down. Our body temperature starts to decrease. That's when this happens. Our muscles relax. Our eyes stop moving. So we're sort of shutting down to go into that deeper sleep. And this is where we start seeing sleep spindles. And so those are going to be very high frequency, short bursts of brain activity. So they last 1 to 2 seconds. They're going to be really dense sort of squiggles of activity, and then the brain goes back to its sleeping stage. We also see something else. If I switch over to a slightly different EEG output here, we can also see K-complexes. And so if we look at that new EEG, we see that we still have our sleep spindles and we still have our background sort of relaxed theta waves, but now we see these big spikes, or one big spike, and that is a K-complex. So it's a sort of intense period of neural excitation and then neural inhibition. So we see a big up and then a big down and then back to normal. So that's something that's a little bit more new in our study of sleep. I've only seen one of my textbooks introduce this, so I figured I'd mention it because I'm sure we'll be learning more about it as time goes on. But this is the first of our studying sleep is an ongoing and evolving process. All right, so we made it through stages 1 and 2. Next, we're going to come into our slow wave sleep. And despite the fact that most texts will divide sleep stages up into 5 separate stages, they tend to group stage 3 and 4 together. I don't know what the point of that is. Why not just condense it, but whatever. So stage 3 and 4 are when we start into slow wave sleep. The way that I've determined it is stage 3 is when we start seeing the appearance of delta waves. So those are really high amplitude and very low frequency. They're very spread out. So that's when they start showing up. And then when we hit stage 4, that's when we are seeing just delta waves. It is dominated by the presence of those delta waves. So when they first start appearing, that's stage 3. When they're everywhere, that's stage 4. And so this stage is really important for us to feel rested. This is that deep sleep where we start recovering and sort of rebuilding anything that was damaged during the day. So this process will start about 15 to 20 minutes after our stage 2 started. So it takes about 30 minutes total to get here after going through 1 and 2, plus or minus a little bit. If you're very quickly dropping into a deep sleep, it might be less, but that's about the rules. And people will usually stay here for about 30 minutes. We will see in a couple of slides that the amount of time that we spend in this slow wave sleep will change over the course of the night. So earlier on, we get more slow wave sleep, and as time goes on, we'll get less and less. But we'll look at that on its own separate graph in a couple of slides. And then the neat thing happens here. So once we've dropped down all the way to these slow wave sleep stages, then the pattern reverses and we start going back up. So we'll come from stage 4 to stage 3 to stage 2, and then instead of sort of going back to stage 1 and waking up, we're going to go into stage 5, which is called REM sleep. And so REM stands for rapid eye movement, and that's because this stage is typically identified by the fact that our eyes move rapidly. So despite the fact that most of our body has the muscles paralyzed so that we can't move around in our sleep, our eyes start moving for this stage in particular. And this is going to be about 20 to 25% of our total night's sleep is spent in this stage. And again, we start seeing that the cycles of REM sleep have differing durations. So we'll start off with very short REM sleep cycles, and then we'll get longer and longer as the night goes on. And then you might have noticed from our visuals on screen here, so we had our stage 4, we had gone into our deepest deep sleep, we would hop back up through the stages, but REM sleep kind of looks familiar, and it looks very different from our other sleep stages. So if we think about it, it looks an awful lot like our brain activity when we're awake. We see a lot of the same patterns. And in fact, our brain looks very similar to an awake brain in that stage. This is one of the reasons why people originally assumed that we dreamed during REM sleep. And we do dream during REM sleep, but it is not the only time that we dream. We can also dream during other sleep stages as well. So this is one of those, we've learned that it isn't just where we dream. And so this diagram, well, 2 diagrams actually, shows all of those stages all together. I kind of zoomed in for each of them to show you the progression, but this is how it looks total. And because different textbooks have different of these images, I like including a couple of them so that you get a more complete view of what we're looking for. So the waves that we've been looking at are a little bit fuzzier, a little bit thicker. The ones on the other side are a little bit finer and easier to visualize, but they're showing us the same basic things. You can tell that the one on your right has that K complex in addition to sleep spindles, so that's where I had pulled that info from. And they do something interesting here where they condense stage 3 and 4 both into slow wave sleep. Some texts do, some texts do, some don't. It is what it is. But yeah, I find that everything else is pretty nice, pretty working well together. So, okay, that's our stages, but I kind of hinted at the fact that we drop into and out of these stages in a particular pattern. And that's where a hypnogram comes in. And this is just a diagram that shows what stage of sleep we're in at different times of the night. So again, we have time on our x-axis at the bottom there, just in hours of sleep. And then our y-axis is which sleep stage we're in. So we can have different kinds of hypnograms. So there's this one from the text that groups our stage 3 and 4 together. We also have this one here from a different text that lets us keep stage 3 and 4 separate. I like this one because it also includes things like our eye movements and the presence of dreams at different stages and times. So we can look at the bottom, seeing that rapid eye movement is most common during our REM stages, as we'd expect from the name. And that we see dreams at all sorts of different stages of sleep. And the way they've been able to figure this out is through sleep studies. So you can have people with an EEG cap on, with a heart rate monitor, with all of those sensors that they want, and they might go in and wake people up throughout the night whenever they hit a particular stage. So maybe they want to learn about stage 2 sleep. So they're going to wait till someone's EEG matches stage 2 sleep, and then they'll go in and wake them up and ask them what they remember. And that's how they figured out that people would be able to remember dreams even in other stages. So it's not just REM sleep that has dreams, we can have them in other places too. But let's look at what's actually going on with our patterns here. So we already kind of mentioned the fact that with our deep sleep, our stages 3 and 4, we find that we have most of our deep sleep early on in the night. And that makes sense. That's our deep restorative recovering sleep. So at the beginning, we'd go dropping down right into stage 4, and we'd stay in that stage for quite a while. But the next time we drop down to stage 4, we don't stay there as long. And then the next time, maybe we don't even go into a deep enough sleep to hit stage 4. Maybe we just stay at stage 3, when those delta waves are sort of present but not everywhere. And then the next time, we don't even hit stage 3, we stay at stage 2. So over time, we have less and less of those deep sleeps because we've recuperated enough. And to make up for that time that we're losing not in deep sleep, we see more and more REM sleep as time goes on. So our first REM sleep cycle, REM 1, is just very short, just say 20 minutes or so. And then REM 2 is longer, and 3 is even longer, and 4 is longer still. So that's us sort of progressively getting closer to being awake. And then we can wake up from any stage here. You're going to feel differently depending on what stage you wake up from. That's why there are sort of a lot of alarms that kind of monitor your movement so that they can get some assumptions about what sleep stages you're in and wake you up at a time when it's going to be less inconvenient. If you get woken up during one of the deeper stages of sleep, that's when you wake up and you feel like you were hit by a truck. Everything is still sort of slowed down, you're still tired, everything's heavy, and that's because you are still in that very deep shut down stage of sleep. But if you wake up, say, during REM sleep, then it's a lot easier to come out of that sleep because your brain waves were already pretty close to awake. So it's a lot nicer to come out of sleep when you're in a lighter sleep stage. And so that's why there's so much push for things like phone apps that register how much you're moving and learning about when it's best to wake you up so that you don't have to have an alarm go off at an inconvenient time. All right, and I think that's what I wanted to say about that. So we can talk about sort of why do we sleep, what's the purpose of it. We'll also be talking about why we dream, what the purpose of that might be. And this is where we get into that idea that there are a lot of different hypotheses, but none of them are necessarily shown to be exactly right. Or we can't say that only one of these is correct. We're more at the stage of each hypothesis can have its own evidence, and we can see merit to each of them, and they might not be mutually exclusive, but we can't really know why we sleep. We might not know why it's evolved. We just know some of the things that happen because we sleep. So we'll talk a little bit about the hypotheses and the evidence that we have that supports each of them, but we're not going to get any final answers. So our first hypothesis of sleep was that we evolved this ability to sleep because it helped conserve our energy. We shut down. So if there's a part of the day that we can't be out gathering food and interacting with our environment because it's dark, then we might as well sort of shut down, save energy, and wait until we can go out and be productive again. The second hypothesis kind of ties into this because when we're shut down, we're specifically not moving. And so if it's dark out, you don't want to be wandering around in the dark. You might attract the attention of predators. So if you're going to be shutting down, why not stay still, stay quiet, and not attract sort of any kind of danger? It also keeps you from moving while you're asleep so that you're not going to wander off into danger. Our third hypothesis is the idea that sleep helps us recover and restore energy. So during the day, we are moving around, we're using our bodies to do things, we're burning energy, and then at the end of the day, we need to kind of reset, restore all of our lost resources, get everything back into functioning order. So sleep might help us with that restoration. And so if we wanted to look at evidence for these, when we sleep, we already saw that our brainwaves slow down. So our brains aren't as sort of close together active. We're seeing a lot slower waves. We have reduced heart rate. We have reduced movement. We have lower body temperature, all of these things. And that all associates with less burning of energy. So we definitely do conserve energy when we sleep. We don't know if that's what caused sleep to evolve, but it definitely happens when we sleep. That immobilization is also logically helpful. So in addition to saving energy, we're not going out and interacting with the world, which is arguably safer. And we do find that if you interrupt people while they're sleeping, especially if you interrupt them during those deep, slow wave sleep sessions, you find that they have a lot of cognitive deficits when they wake up. So if you don't let someone have really deep sleep, then they're going to be tired the next day. Their thinking is going to be a little bit slower. They're going to have trouble making connections and stuff like that. So there seems to be some element of evidence for each of these, which is why we have all of them here. So we can't necessarily know the answer in this case. If we wanted to talk about functions of specific parts of our sleep, we already kind of mentioned that the slow wave sleep is really good for that restoration and recuperation of both our brain and our body. And we mentioned already that that sleep deprivation can cause cognitive defects, or deficits, sorry. So that kind of makes sense. That seems to be what our slow wave sleep is doing. REM sleep also seems to have some function to it. So the idea here is that it's involved in memory consolidation. And we'll talk about that in a chapter on memory. But consolidation is basically the process of taking all of the things that you do and encounter during the day, deciding what's important, and storing it away in your long-term storage. So consolidation is that process of taking the important stuff and putting it somewhere so you can remember it later. And so if people don't have REM sleep, then their memory will suffer. And there's also something called the rebound phenomenon, which shows that if you have people, again, in a sleep study, and every time they fall into REM sleep, you wake them up. So you prevent them from having REM sleep for long periods of time. As soon as they're allowed to sleep without being disturbed, they have much more REM sleep than they would have usually. So we see sort of an overcompensation for missing out on that REM sleep. And so the idea is that, okay, well, if our body sort of makes up for lost REM sleep, then it must be important for something. What exactly, we're not positive of, but for now we think it has something to do with memory. All right, and that's kind of a nice way to transition over into talking about sleep deprivation. So we, as researchers, can interrupt different stages of sleep and deprive people selectively of particular stages, but we also have the tendency to experience general sleep deprivation. So maybe you had a big paper due and you weren't able to sleep overnight. So what happens when you miss out on that required amount of sleep? So that's when we run into this sleep deprivation. And you can accumulate sleep loss not just in one day, but you can accumulate it over multiple days. As students, I'm sure we've all experienced pretty bad sleep debt. So maybe you have a bunch of midterms coming up. And so instead of sleeping the sort of 7 to 10 hours that you should sleep each night, you're only getting 6 hours for a whole week. So you end up accumulating a lot of sleep debt. There's sort of a misconception that any sleep debt that you incur has to be paid back in full. So if you miss 5 hours of sleep, then the next night you're going to sleep an extra 5 hours. That's not really supported by evidence, and you've probably experienced this. So if you have a whole week where you're sleeping a lot less, maybe you've built up a whole 24 hours of sleep debt. You're not going to then lay down and sleep for more than a full day. You're probably going to sleep a little bit longer than usual, maybe 10 to 12 hours, but it's not usually going to be a full payback of it. So that's just one of those misconceptions that I commonly see. And I did mention that people tend to get between 7 and 10 hours a day. When you're a child, you get a lot more than that, and as you get older, you need a lot less, into old age where you only need like 6 hours or so, which is kind of interesting to note. There's also a well-known genetic mutation, just in case you're curious. It is DEC2 is the gene that's involved, and people who have a mutation in that gene require significantly less sleep. These are the people that can get by with like 3 to 5 hours of sleep every night and be perfectly fine. So there's a genetic reason for it, and I don't know how they manage to be that lucky, but there are a non-insignificant amount of people who have it. So kind of interesting. I myself happen to be on that high end of the scale. I need like 9 or 10 hours of sleep to be functional, which was particularly problematic when I was a student. All right, and of course, if we're going to talk about sleep, we obviously need to talk about sleep disorders. So there are tons of sleep disorders. We're going to hit some of the high points. We're not going to go into tons of detail, but mostly just the ones that I find interesting or know a lot about already. So insomnia is the most common sleep disorder. This is the inability to fall asleep or the inability to remain asleep. And that's another one of those misconceptions. Some people have insomnia and don't realize it because they don't have any problem falling asleep. Their issue is staying asleep. Maybe they wake up 2, 3, 5 times a night. And each time they can fall back asleep fairly quickly, but the fact that their body keeps waking them up prevents them from having a normal sleep cycle, prevents them from getting all of that deep sleep that they need, and it can still be problematic. So that can be insomnia, even if it doesn't fit our sort of mental idea of what insomnia is. We can also have different kinds of insomnia based on the source of it. So conditioned insomnia comes from conditioning, things that we've learned, associations that we've made, and experiences that we've had. So a great example of this is maybe as a student, for years and years, you had to get up really, really early to catch a bus to go to school. I lived in an area that didn't even have a bus into the city, so I had to get up early to drive to the nearest town, to get on the bus, to sit on the bus for 2 hours for an 8 a.m. class. So for the longest time, for years afterwards, I'd get up at 5 in the morning. I didn't work until 9 o'clock, but I was up at 5. So it was conditioning and experience that led me to waking up a lot earlier than I needed to. And you might even have that with falling asleep. Maybe you should go to bed early because you work in the morning, but you're used to staying up late, so you're going to stay up late even though it means you get less sleep overall. So we can have these conditioned learning experiences that influence our sleep and can lead us to have less sleep than maybe we should. You can also have idiopathic insomnia, and that's when it's caused by some kind of abnormality. So if there's damage to the brain, this can be something that's congenital, something that happens sort of from birth. It can be due to damage. There's a lot of ways that you can have this, but it's sort of with a physical cause that they can point to. We can also go in the opposite direction and have hypersomnia, which is excessive sleepiness. And there's a little bit of an asterisk there. It's excessive sleepiness with no legitimate cause, or with no sort of surface level cause. So this could be due to overproduction of melatonin or something like that in the body. That's something that could cause hypersomnia. But if, as a student, you're just overworked and undersleeping and always tired, that doesn't count as hypersomnia because there's a reason for it, and it's a behavioral issue. All right, so that was insomnia. That's our most common one. We can also have narcolepsy, and that's individuals who fall asleep uncontrollably. Narcolepsy is a really interesting one, and some cases of narcolepsy can be genetic. In fact, researchers have bred specific lines of different organisms that have narcolepsy so that they can study it. So you've probably seen YouTube videos of the species of goat that has narcolepsy. It's not every single goat of that particular breed, but it's a very high number of them have a gene that predisposes them to narcolepsy. And so you can have an entire herd of goats running around, and periodically one of them will just sort of flop over and a couple minutes later get back up again. So this is that uncontrolled urge to fall asleep, and it can happen pretty much instantly. There are also, of course, lines of mice and rats that have been bred to have this. There are also, I think, dogs with the same deficit as well. So they know some of the genes that are involved in it. There can, again, be sort of physiological issues as well as genetic ones that can cause it. But if you think about it practically, as a bipedal organism, humans with narcolepsy are at high risk of damage. So if you're walking around between classes and all of a sudden you fall asleep, your knees might give out. You might face plant on the ground. So for people who have like very rapid onset narcolepsy, it can be really dangerous. And one of the most common injuries that they have is actually to break their jaw because they'll hit their chin on whatever they fall forward onto. So they might have to start wearing protective gear to make sure that they don't do that while moving around. If they have sort of a little bit of warning, maybe they start feeling sleepy before it happens, then they can kind of overcome some of those things, but people don't always get warning of it. We can also talk about sleep apnea, and this is a reflexive gasping for air that happens when people are sleeping. Basically, if you think about when you're sleeping, especially on your back, you might notice that you are a lot more likely to snore when you sleep on your back, and that's because you've relaxed all the muscles and everything in your throat. And so with sleep apnea, it's almost a more extreme version of that, where you've relaxed to the point that you aren't able to get air through all of those structures and into your lungs. So what happens is when your brain realizes that you're not getting oxygen, you get awake enough to take a sort of deep, deep breath of air to sort of recover from that, and then you'll go back to sleep. And so individuals with sleep apnea can do this hundreds of times a night. And if you're waking up every single time to take that deep breath of air, even if you're not fully conscious of it, you're still interrupting that deep sleep. And so even if you sleep for the right number of hours, you might wake up exhausted because you didn't get any of that recovering slow wave sleep. And so there's lots of ways around this. It can help for like low levels of it, just sleeping on your side. But there's also sort of sleep apnea masks that you can get. So either full face masks or even just your nose. And they help provide a little bit of air pressure to keep all of the structures open and getting air into your lungs. And there's been a lot of really neat advances in that field, just a personal observation, where it used to be that it was sort of a constant high flow air pushed in your face all the time, but now they are smart and they predict sort of how often you need a breath of air, and so it'll pulse and push air into your lungs and then relax so that you can breathe out. So there's lots of new technologies helping with some of these issues. Our next two disorders to mention are nightmares and night terrors, which are not identical. Nightmares are just anxiety-arousing dreams. So things that make you anxious. So maybe you have a bad dream, it scares you, and you wake up and you feel afraid for a few moments, but then you're going to calm down and go back to sleep. A night terror is sort of a more extreme version of that. So this is intense arousal and panic. So this is when it triggers that fight or flight response in your body. So people with night terrors might wake up and run. They might flee. They might not even know why they're afraid, but they have this full body feeling of panic and the desire to be doing something with it. And with night terrors, it's going to take a lot longer to calm down to be able to go back to sleep. You can also have sleepwalking, so that's something that is fairly common in children. As we get older, it's a lot less likely to sleepwalk, so a lot of people who did it as children might grow out of it, but it's not always the case. We also have sort of REM sleep behavior disorders. We can talk about the fact that, kind of mentioned that we have muscle paralysis when we fall asleep. So as our muscles stop moving, they kind of disengage so that when our brain is dreaming, so when we're in some of those other stages and having dreams, our brain can fire as per normal, but our body doesn't respond. So you can have a dream about soccer, but not kick out in bed. So some REM sleep behavior disorders basically mean that you don't disable some of the muscles that are involved, and you can end up acting out your dreams, which can be disruptive if you sleep with someone, but can also be very exhausting because you're using extra energy while sleeping. So a whole bunch of different disorders, but those are sort of my high points. Our next couple of topics are all around dreaming. So dreams are just mental experiences that we have during sleep. And this is one of those, again, areas that we don't know a whole lot about what's going on. So the content of dreams are usually familiar, but not always. So you might dream about things that you've done recently, or situations that you're familiar with. Or you might have dreams that are completely different, entirely out of left field. So there's a lot of different options there, but we typically see stuff that we have some experience with. People have common themes between their dreams. This is why you see a lot of those sleep analysis posts or books where they talk about, oh, if you dream about all of your teeth falling out, it means this. And if you dream about all of your hair being gone, then it means that. There are some of these sort of themes that repeat consistently. And some people will associate sort of meaning and interpret them to mean something important. Other people, not so much. When Freud started looking at dreams, and we'll talk a little bit about some of his very interesting dream theories, he talked about dreams as day residue, sort of spillover from our daily life. So if you're working on a paper and then you go to sleep, you might dream about the topics of that paper. So it's just sort of stuff carrying over into your unconscious mind. We also have the possibility for lucid dreaming. And this is something that you can actually learn to do, where as you're dreaming, you become aware of the fact that you're dreaming and then can control what you dream about. So that's an interesting topic. And then there's sort of some cool concepts about differences and similarities between cultures when it comes to dreams. And as we've said, there are a lot of similar themes, a lot of similar motifs that show up sort of regardless of what part of the world you're from. We can call dreaming a pretty much universal experience because there are studies that have shown that even people who are blind from birth, they still dream. It isn't necessarily the same visual stimuli that we associate with dreaming, but they do still have dreams of the same vein. So it's something that seems to be universal across all humans, no matter what. Where we see differences with cultures, it might be, say, the importance assigned to dreams based on sort of social factors and things like that. And different topics might be a little bit more common because it's probably what you're more familiar with, but for the most part it seems to be pretty consistent. And so now for the cool part, we get to talk about why we might dream. So some of our cool theories of dreaming. And we can always start with Freud because it's going to be so different from anything else we talk about. But Freud talked about dreams as the guardians of our sleep. So basically, dreams were our protectors. And if you remember, Freud was really focused on the fact that our unconscious mind was full of these deep, dark desires and sexual and aggressive urges and things that were sort of trying to get loose. And so when we're awake, our mind would be able to sort of keep all of that at bay. We're not aware of our unconscious, no big deal. So the part of our brain that would be censoring out all of that stuff from our unconscious is called the ego. And when we're asleep, the ego starts to relax. It is less able to keep all of those things at bay, and so they start coming out in our dreams. And so Freud argued that this outlet, having all of these weird desires come out in our dreams, sort of let us burn off that energy and protected us, made it capable for us to block them out when we woke up and went about our days the next day. So he called this sort of wish fulfillment, where our minds could act out all the stuff that we couldn't do while we were awake, and it protected us by letting us sort of function normally in society. Obviously, that isn't necessarily what we think is going on with dreams, but as per usual, it's interesting to point out Freud's perspective because it got enough other people involved with their own theories that it gives us other topics to discuss. The next is the activation synthesis theory, and this is basically the idea that we dream because our brains are doing things. So it isn't repressed desire, it isn't us acting out stuff, it's just our brains doing things in the background and us assigning meaning to what is essentially random firing of neurons. So if we think about it, we have all of these neurotransmitters and things moving around in our brains. When we sleep and we're recovering, stuff might be moving around. We might be resetting or moving neurotransmitters or whatever. And so we end up with a very haphazard and chaotic pattern of neural firing as we do whatever it is we do while we sleep. And our forebrain is responsible for assigning meaning to stuff while we're awake, and it doesn't necessarily turn off while we're asleep. So it could listen to all of these firing neurons and say, okay, well, the back of your brain, that visual cortex, is firing as though you're seeing this. So I'm going to see this. And that could explain why we end up with really strange and disordered experiences, because our forebrain is trying to make sense of random firing. So dream logic is different because it's not really based on actual logic, it's just based on trying to make sense of what it's presented with. And of course, we don't necessarily have evidence for this. You can't prove that that's what's going on. We do know that our brain fires fairly randomly while asleep, so it makes sense that we could be turning it into what we dream about, but we're not quite sure as of yet. We can talk about our evolutionary hypothesis of dreams, which talks about sort of what it accomplishes to dream. And this is the idea that what we dream about has some kind of biological relevance. So we evolve this ability to dream because it helps us survive by sort of reinforcing important life skills. And so that kind of ties back to that idea of solidifying memories, where if you're learning to do something like cook for yourself, that's an important life skill. So maybe you're going to dream about it to help you store that memory, consolidate it for later, so that you remember that task and can perform it better in the future. So you would be a lot more likely to dream about things that are relevant to your survival. Again, we can't really get evidence for that, but it's a possibility. On the cognitive side of things, we can talk about dreams as a way that we problem solve. So if we think about it, when we're awake and actively trying to solve a problem, we're constrained by our own interpretation of the situation. So we have pre-existing knowledge and established rules that determine how we tend to shape and frame problems. But when we sleep, we aren't necessarily constrained by those same rules. So dreaming might provide us with a nice creative way to solve problems outside of our normal constraints. Or we could just say that we have this cognitive process where when we're awake, our brain fires in particular patterns, and it does that all day, every day. So when we go to sleep, it doesn't stop doing what it was doing. So we stop acting out those firings, but they're still happening. So that's what dreams are, is just the interpretation of our body continuing to do what it was doing while we were awake. So again, none of these are necessarily accurate or mutually exclusive, but a couple of possibilities as to why we might dream. And that is a perfect spot to stop, because we then have our next topic, which is alterations of consciousness. And that'll be the last topic for this chapter. So I will let you guys go. Have a phenomenal weekend, and I will see you on Monday.